All right, so let's revisit Atwood. Same question. What is linear acceleration of object A and B? Let's imagine we know MA, we know MB. Let's imagine that MA and MB are known in such a way that A is going down the inclined plane. So we know the direction of motion as usual. The new piece of information is MP. Now we have to consider the pulley. All right, alpha is given, friction on the inclined plane as usual. So same question. The only new thing is now we're not dealing with the massless pulley. As soon as you see that the mass of the pulley is given, we have to consider it. Before we do this, let's do a little on the side. Let's focus on that stupid pulley. Now that we know about rotation. Remember, if we do a free diagram on the pulley, what are we going to have? The weight of the pulley, the normal force from the axle on the pulley, that stupid number force, I have no idea where it is, but it's somewhere in here, and then the two tensions, TB and TA. This pulley is rotating about 0.0. When we consider the massless pulley, and we didn't consider rotation, we said that TA was equal to TB. Now let's see and appreciate why or how we can't do this anymore. Let's use the same reasoning as the rotating wheel, up the ramp or down the ramp. If that pulley rotates about 0.0, which is also located at its center of mass, obviously the weight nor the normal force can create an angular acceleration. It's got to be the tension. We've seen with pulley, it's easy. It's always perpendicular. So T is creating an acceleration clockwise, and TB, and TA opposite. But they have the same position vector R because it's a pulley. So the torque due to TB is RTB, negative, and the torque due to TA is RTA, positive. If we continue to assume this, we have a serious problem, because the sum of the torque of all those forces about point A is 0. But if our system is accelerating, and that's what we're looking for, then A is accelerating down, B is accelerating up, then the pulley must be accelerating with alpha. But this tells us that alpha is 0, because this plus this, if T is equal to TB, will give us 0. So we have 0 plus RT minus RT. Everything is 0. So obviously that can't be right. So that's the condition we're going to lose. Now that we understand torque and rotation, if the direction of motion of A is to go down the inclined plane and B is to go up, obviously the direction of alpha is to be counterclockwise, which means that TA has to be bigger than TB, so that the torque created by TA is bigger than the torque created by TB, because there's those only two torques that can create that rotation. If object B was going down with a linear acceleration, then TB would have to be bigger than TA. All right, so now that we understand conceptually what's going on, let's see how the system differs with considering the mass of that stupid pulley. No problem. 90% of this problem is from chapter 5 and chapter 6. We know how to master pulley with Newton, Atwood with Newton. We're going to see that we just need one more equation. No biggie. So we master on this. Let's go fast. I'm going to pick a coordinate system for B, which is positive up. As usual, I'm going to follow my direction of motion. Same for A. A is going down. I'm going to put positive X down. Again, nothing on the trees. And I'm going to consider the positive rotation for my pulley to be counterclockwise in order to be consistent with the coordinate system of my two other. This will allow me to have positive MA and I alpha for all my systems. You don't have to do this, but if you don't, you're going to have to insert a negative sign, which most people forget. So be consistent same as chapter 5 and chapter 6. Pick your positive direction in the same direction as your acceleration, which in this case is obvious. Free body diagram. Again, let's review real fast. This is MAG. This is TA. This is NA. Object is going down, therefore this is mu K NA. All right. B, MPG. This is TB. And this is alpha. All right. Let's apply Newton's second law to all the translating system. We have three systems, A and B, and both are translating. So for any translating system, we're still going to use sum of forces equal to MA. Nothing changes. Therefore, we're going to have MAG sine alpha minus TA minus mu KNA. And this is equal to MAA. Same as before, except we're going to keep TA. In the Y, NA minus MAG cosine alpha. That's equal to 0 because there's no acceleration in my y-axis. And then for object B, TB is more power than MB, negative MPG, and this is equal to MBA. So exactly the same equations before. The only difference now is we cannot substitute T and TB as T, which means we're dealing with NA, A, TA, and TB. That's 4 unknown. We only have 3 equations. We need 1 more equation. Since we've done system A and system B, we have identified a third massive system, pulley. The pulley is rotating. Therefore, we cannot apply sum of the forces equal to MA, but we can apply sum of the torque is equal to I alpha. Let's do that. As we just saw earlier, the only 2 forces that will create torque about point O is TB and TA. The weight of the pulley and the normal force from the axle on the pulley do not create any work because the position vector is 0. TB is going to tend to create a torque which is negative in this case because I was assumed to be positive counterclockwise, but TA will be the positive one. Therefore, R, which is the radius of the pulley, and that's something that may or may not be given to us, we'll see, times TA, positive rotation, minus RTB is equal to I alpha. We just got our 4th equation. That's perfect. The problem is we have introduced 2 more unknown, I and alpha. So now we have 6 unknown and 4 equations. No worries. We know how to get those 2 little buggers. What is alpha with respect to A? Well, it's a basic definition. We've seen this many times. Bang, problem solved. So we can substitute alpha in terms of A, it disappears. When we don't it out, well, no problem. This is a pulley, which rotates about its center of mass. Therefore, by definition, 1/2 mass of the pulley, radius of the pulley squared. Done. Now we can substitute all this. Let's do it once. The rest is just math. You have 1, 2, 3, 4 equations for unknown with those 2. So as you substitute those 2 here, you have RTA minus RTB is equal to 1/2 mass of the pulley, radius squared, and alpha is A over R. Look what's going to happen. Hurry up. We don't even care about R. So we're down to 1, 2, 3, 4 equation for unknown. Okay? Let's solve for T on the first one, TB on the second one, and let's substitute in the last one. So as we solve for T on the first equation and substitute it in the 4th equation, we end up with MAG sine alpha minus mu Kn, and NA is MAG cosine alpha minus MAA. That's the first term right here. Minus TB. TB has two terms, so we need to distribute the negative sign to both terms. From equation 3, we can solve for TB. TB is equal to MBA minus MBG. And the whole thing is equal to 1/2 MPA. That's it. Now let's solve for A. As you solve for A and extract A, move this bugger and this bugger on the right-hand side, factor out the A, divide by whatever is left, and that's it. We're done. So we have MA. G is going to be everywhere, so sine alpha, negative mu k, MA cosine alpha, negative MB times G, and we're going to divide by the total inertia, which is MA plus MB plus 1/2 MP. I really hope you save all those Atwood problems from both energy and Newton, so you should have it on your notes. Just flip back your notes, look at the functional form of this, compare to chapter 5, and you will see that the only difference is this little bugger. Up!